All right, so this week we're going to be doing deep reinforcement learning and generative adversarial networks. Just a note on logistics. So for the quiz that was due yesterday at midnight, Arvind extended the deadline, so it'll be due today at midnight instead. So if you didn't get a chance to do it before now, just make sure you do that before the end of today. The homework for this week will be due a week after the homework for week 6 is due. And the quiz for this week will be due a week from now as well. So yeah, are there any questions about logistics before I get into the lecture content, or are we good? Okay, great. So this week, we might actually have a little bit of a shorter lecture than usual, just because like on an executive level, we decided that we shouldn't go as deep into the actual workings of the concept that we're covering this week because they tend to be very, very complicated, especially reinforcement learning. There's a lot of different subfields, which we felt would not be like able to, we wouldn't be able to condense it into one lecture. So we might be a bit on the shorter side today. So just keep that in mind. So yeah, first a bit of a recap on some neural network concepts. So this is from week 4, week 5. So a neural network, again, is just simply a bunch of neurons connected together in specific structures, and the way you choose to put them together affects the information and whatever your neural network is learning as its output. And as a reminder, neuron itself is just simply like a linear equation taken with an activation function to some other nonlinear number. And that's essentially what a neuron is. And so we also did, we covered this in week 5 as well, a backpropagation, which is essentially the way to calculate how every single weight in your neural network affects the loss, and how you can change those weights in order to decrease the loss as you train your neural network. And so the way you do this is you just use the chain rule and you move backwards through the network, hence the name backward propagation. And then you do this until you fully calculate how each weight should be updated. And so this is just like the basic example, sorry, not example, basic method for how neural networks actually compute and actually learn things. This is the main component of it. The second part is gradient descent, which is the way you actually reduce the loss. But that's just another topic. Next, we have convolutions. So again, a convolution is a process of taking a kernel, which we defined as like, we can define it as like a predefined filter, which is used to extract certain features from a network. I showed the example in week 5 of a kernel that was used to extract vertical lines from an image. But the point of a convolutional neural network is to learn different filters that you want to use in your final output. And so those filters could be anything from here's a horizontal line to here's a diagonal line. Things like that are all possible examples of filters. And the job of your convolutional neural network through this process of convolutions is to take those filters and run it over the original input, ensuring that the final output is something reasonable that you want based on whatever problem you're training it for. And finally, we have a recap of autoencoders. So autoencoders are a type of deep neural network, which they're composed of 2 separate neural networks, which allows for the entire neural network to develop a compressed representation of whatever the input is. In particular, the key feature of the autoencoder is that the input and the output should be the exact same, as in this is a unsupervised learning method, so it doesn't require labels for the input data. And so in terms of recommendation systems in particular, they're used to reduce data dimensionality for other analysis. And this will be particularly important for a discussion on GANs, which I'll get into later. But it's just a good reminder of the fact that you can have a neural network that is sort of composed of 2 different components. All right. Are there any questions on the recap so far? We won't be going into RNNs since that was still fresh from last week, but yeah, any questions so far? Okay. All right. So first thing we're going to go into then is reinforcement learning. So what is reinforcement learning, right? So RL, as it's otherwise known, it's a type of machine learning technique where you have some sort of agent, which is in an environment, and it learns by trial and error using the feedback from its actions and what it experiences in the environment. And so it's meant to sort of replicate how humans kind of learn rather than directly simulating, the brain of a human being as most deep neural networks do. Machine learning is a type of machine learning where you sort of experiment the process by which a human learns. And it does tend to use deep neural networks as well, but in a different manner. And so it falls kind of in between supervised and unsupervised learning in that way. So it doesn't rely on a set of labeled data in particular, because you're not saying like, I want this output for this particular input, but it's also not unsupervised, since you are telling it like, this is wrong, this is right, or this is good, or this is bad. And that the thing that I just said, where this is wrong, this is right, that's called a reward function, which is what reinforcement algorithms desire to optimize. And you can think of it sort of like as analogous to a loss function, but not quite a loss function. So it's not running on a set of label data, but rather on sort of like an environment and a state for the agent. So before we go into like the details, it'd be good to get an example of RL, since I find it's easier to think about RL when you're thinking about it in terms of an example. So one of the most prominent examples of this in practice is AlphaGo. So the agent in AlphaGo, or sorry, for those of you who don't know AlphaGo, it's a deep neural network trained by DeepMind, I think. So it was tasked with learning how to play Go. It ended up being beating the world champion, I believe, in Go. And so Go is a really complicated game, or rather, it's not complicated, but it is complicated for strategy. The rules itself are pretty simple, but the strategy tends to be very complicated. And so it was difficult to write a direct neural network for its task. And so the people who made AlphaGo decided to go with the deep reinforcement learning approach. And so the idea was that the agent AlphaGo would be given an environment consisting of the game board state and the moves it could make, and was just tasked with optimizing a reward function, which was whether the agent won the game or not. And so it learned based off that over many, many trials how to play Go. And so that's an example in this case. So just to recap the terms I talked about last slide, the agent in this case is the algorithm, AlphaGo. The environment in this case is the game board. And the state is what pieces and what possible moves you can make on that board. So that's an example for reinforcement learning. So key terms. Reinforcement learning algorithms use the concept of an agent, which is an actor that decides actions based off the environment and the reward function. So like I mentioned last slide, it's basically the way which we're learning what we do, or rather what is learning. And so one thing that isn't clear throughout all this yet is, how do you define the reward function, or what is the reward function? So just to fully specify it, the reward function, it's a feedback signal which indicates how well the agent is doing at a certain time. In this case, we're referring to time in the context of like a state for our game board. So for example, like at move 1, say in like a game of Go, the reward function indicates how well the agent is doing. So it indicates maybe the likelihood of it winning in that state, or something similar to that. And for example, if we're playing Go, the reward function could be an indicator for whether we won or not. You wouldn't likely use that in practice, because you wouldn't be able to learn anything until the game ended, because it would be 0 until then. But yeah, so that's an example of a reward function. Any questions so far? All right, so we'll move on. And so since the agent makes decisions at every step in this process, you can think of that like, at every step in a game of Go or in a game of chess, you have to make a certain move. And sometimes the actions that you make very early on may have a long-term consequence on your overall goal. So for example, for those of you who are familiar with chess, if I play like h4 at the very beginning, at the very beginning, it's not like a particularly bad move per se, it's completely valid. But you would observe, because over a long-term consequence and a long-term time, that it's very bad for your game, and you would probably end up losing if you played h4. And so and other terms and other cases are that it sometimes may be better to sacrifice like an immediate reward to gain more long-term reward. An example of that would be in chess. So you could sacrifice a pawn to capture a rook at a later stage in the game. And so you need to define your problem such that you don't necessarily want to maximize reward at immediate, like in the short term, because it's not always necessarily the most optimal. So it's not like a greedy algorithm approach. You don't want to always get the best thing. You want to maximize the overall thing. And so you need to define, when you're defining a reinforcement learning problem, you want to define it such that it satisfies something called the reward hypothesis, which is the idea that all goals can be described by the maximization of expected cumulative rewards, or essentially the idea is that the total reward that you get, you want to maximize that. And so that's how you sort of define, what do you use sort of to define the reward function? Any questions on that? All right, great. And so now we go into something called the RL process here. So if you look at this map, you can think of sort of the brain here as the agent in this sort of RL formulation here. The environment would be the maze that we're looking at here. And the state would be where we are in the maze at a given time. And so the idea is that at every step, the agent will make some sort of action, right? And it'll make that based off the previous observation and reward. And then once it's made that action, the environment will update based on the action. So for example, if I start at this red arrow, and then I move down to here, the state updates to reflect that, which is independent of the action, which is independent of the agent. So the agent doesn't know exactly what is going on in the environment necessarily. And then the environment will return an observation to the agent. And the idea is that basically the agent is able to derive some sort of information from the environment. The reason we formulate it like this, rather than giving the agent direct knowledge of the environment and the state, is because in some cases, you don't always know every single thing about the environment. So for example, if we're thinking about a self-driving car, it's impossible to directly simulate everything that could happen in a car, meaning that the agent, which is controlling the car, cannot possibly know the exact state of the car at any given time. But the idea is that by using sensors to get different aspects from the environment or different observations, like the velocity of the car, the heading of the car, things like that, you can formulate an observation about the environment and then use that to develop the next action. And so that's sort of the idea here, is that the agent isn't given direct control over the environment or direct full knowledge of the environment, because you don't always know that. The environment will also return a reward R based on whatever the reward function you choose to define. For this case, it could be getting to the destination without getting lost, and actually similar for a self-driving car, and based off that, then the agent will make the next action. And so this is just the general process on how a reinforcement learning algorithm learns. And so does anyone have any questions on that before we move on? Sorry, I haven't been checking chat, but okay. All right, so I guess we'll move on then. So basically, after receiving an action, the environment will output a new observation and reward calculation based on that action, and it will also update its state based on everything that happened up until that time. And so we define two I've already been talking about state quite a lot, so I'll just go over that one first. So state is the information that's used to determine what happens next, or rather it's basically how the environment sort of variables are configured at a given point in time. And the history of an environment is everything basically that's happened until that time t. And so yeah. The next thing we'll talk about is sort of a deep dive into state itself. So there are sort of a couple different types of states that we can look at here. So I've been talking mainly about the environment states. So I'll start off with that one. So the environment state is just the environment's internal representation. So, in the context of Go, it could be the current number of pieces of each color and where they are on the Go board. For a self-driving car, it could be where it is in terms of GPS location, how much distance it has between the car in front of it and it itself, how fast it's going, things like that can all be examples of things that are represented in the environment's state. And so this state, like I was mentioning before, may not be fully visible to the agent. And so it's used to pick whatever observation you want to send to the agent. And the idea is that the state will simulate everything for the agent, but then the agent will only get either a certain bit of it or the full information of the state to choose the next action. And analogously, you could also define a state for the agent, which is used by the agent to pick the next action it takes. It's a bit more difficult to define this with like a concrete example, but you can think of it as a similar thing to the environment state, except for the agent. All right, we can also next go into different types of environments. And so this is like, again, a continuation of what I was going on before. But you can have an environment that's fully observable. And the idea behind this is that the agent just observes the environment state. And so it can just use that to fully determine the next action. Not fully determine, but use the full context of information that it has to get the next action. So in the case of AlphaGo, the environment was fully observable since all the information is available to both players. And you can also have partially observable environments. So again, this is the example of the self-driving car. So, you can't get every single bit of info about the environment that you're in for self-driving cars. So you need to use like a sensor to get observations about it. All right. So we've kind of done the setup, for how we set up all these things that we need to learn, but we have yet to actually learn anything yet, So the idea is that now we want to define the things that make the agent capable of taking in an observation and a reward function and choosing the next action. So most RL agents are made up of three components. So those are policy, value function, and model. So policy is the function in an agent, which is a map from a state to an action. So this will take an environment state and turn it into some sort of action. The value function is the agent's representation of how good each state and or action is. And so that's pretty self-explanatory. It's basically just a function that will look at how good each action could be. This value function is developed by the agent, as you go along. Obviously, if we gave it to it, we wouldn't really be learning anything. Yeah. And then the model is the agent's representation of the environment. So it's derived off of the observation it gets from the state, which may or may not be the environment itself, depending again on if we have, a fully observable environment or a partially observable environment. All right, any questions on this so far? I understand it's a bit abstract right now since, or rather it's a bit abstract since we're not really going into all the math, but yeah, any questions? Okay, great. So there are two fundamental problems in reinforcement learning. So those are learning and planning. So in learning, the idea is that the environment is basically initially unknown and the agent needs to interact with the environment to improve its policy. As in like the environment that the agent knows about is initially unknown. So if the environment is not fully observable by the agent, then the agent needs to, develop some model in its head of what it's looking at in order to make sure that it can choose a good action. So that's learning. And then planning is the idea that if the environment is known, then the agent, has to perform different iterations within its own internal model, and then improve its policy in that sense. So there's sort of two components to it. You have to learn what you're looking at, and then you have to learn, what to do with what you're looking at. So the agent, in essence, needs to learn from its experiences in the environment in order to make decisions without losing too much reward. So it needs to consider these two different concepts, which are exploitation and exploration, with a balance between exploring new information and using known information to maximize rewards. So to summarize those two concepts, the idea is that, you can't, if you don't know anything about the environment, trying to improve the policy based off that environment is not going to help. And then, if you fully know the environment, or sorry, rather, if you just keep on trying to fully know the environment, then you're not going to be able to do anything necessarily with the policy if you just solely focus on improving the environment. So the idea is that you need to explore by trying to get new information from the environment and determining what the environment model looks like in your head. And you also need to exploit that information by using it to improve your policy. And so there's sort of two components to reinforcement learning. Does that make sense to everyone so far? Right, great. So, sorry. Okay, all right, thanks. All right, so this week I'm not actually sure if Andre did this last week, but we're gonna be looking at a couple different papers this week. And actually for the homework this week, I made it a bit lighter than usual. So the homework just, I'll talk about it at the end, but one of the papers you'll be reading this week is this paper by Peter Abil, who's, at Berkeley. It's called RL squared, fast reinforcement learning by slow reinforcement learning. So we're just going to go briefly into the premise of the paper to show you what research is being done in reinforcement learning in order to improve them. Because, like I said, we're not really going into all the math behind it, since it can be really, really complicated, even more so than like convolutional neural networks. So, and we figured it wouldn't fit in this time period, but yeah. So the premise of this paper that you'll be reading this week is that reinforcement algorithms attempt to learn the entirety of information that they need for every new task. So you know how I was mentioning last slide about how reinforcement learning algorithms need to learn both information about the environment and information on how to act on it. And so the issue is that for a given reinforcement learning problem, learning algorithms currently tend to just learn everything about it. So if I made one reinforcement learning algorithm to learn, how to play Pong, the idea is that if I wanted to do a different reinforcement learning algorithm to learn, maybe just how to bounce a ball, the issue is that it would have to relearn every single thing about how the physics of that work in order to do the second problem, when we already do have an algorithm that sort of already knows kind of the physics behind how a ball works. And so the idea is that this is really slow for most cases, because you're just relearning a ton of things that you already know. And so for most RL algorithms, you require a ton of iterations in order to produce a meaningful output. And so the idea behind this paper is that you use a new model where you sort of create algorithms that learn basic concepts really slowly, i.e. off of like a few iterations, which can then help other algorithms learn a lot faster. Or sorry, that I had that the other way. You create algorithms to learn slowly, using a lot of information to learn very simple concepts, which can then help other algorithms learn more complicated things in a simple manner. And so the idea is essentially to treat the problem of learning a reinforcement learning algorithm for a given problem as a reinforcement learning problem itself, which is hence the reason behind the name RL squared. It makes a bit more sense in the paper the way they say that. It's a bit hard to describe that the way I have it here. So, when you read it later this week, just if you have any questions about that, you can put it in Piazza. But yeah, so the intermediate result of the first RL algorithms that are used to train this RL squared thing is stored in an RNN, which we covered last week, which is then used in conjunction with the second one in order to produce an output for a given problem. And so if I use the example I had before, if I made a slow RL algorithm to learn the physics of how bouncing a ball works, the idea is to then use that, store it in RNN, and then use that in conjunction with another RL algorithm in order to learn how to play Pong or something like that. And so the paper shows that this approach has been shown to scale well and helps to reduce the number of iterations needed to train RL algorithms in practice. And so this is just kind of sort of an example of how RL is used, or rather how research in RL is, heading. All right, any questions on that? We'll be going into the GAN section next. So yeah. All right, great. Oh, sorry, I forgot about this slide. Yeah, actually, back step. Like I said a ton of times before, we basically need a full separate course in order to go over every single detail about reinforcement learning systems. So for this course, we just define the basic concepts, and we're gonna look at a couple different ways for how they're used in practice. So in recommendation, our algorithms, they view like the recommendation process as sort of like sequentially, where the output of the last recommendation that you had or you gave to a user influences the next result. So it's something that's real life example of this would be music suggestion algorithms. So if I suggest you a song on Spotify and you repeat it or something and you play it a lot again, then the idea is that RL algorithms could use that input, as in like how long you played it, how long you listened to it, if you repeated it, as an input into the next recommendation that it gives you. So it could recommend something from a similar band or the same album, things like that. And so that's how our algorithms could be used in practice. However, it's still a field that is really being explored for its potential applications and recommendation systems. So a lot remains to be seen in terms of what can be possible with R. All right. Now we're going into generative adversarial networks. So generative adversarial networks, or GANs, they're a subset of generative networks which use a secondary adversarial network to aid in generation. So I'll explain that fully a bit later, but the idea is that generative networks are a form of unsupervised learning which use supervised loss functions in order to determine how close the output that you're getting from it is to the desired one. So they're a function that learns how to transform a random probability distribution that they're given into the desired one. The idea is basically that you can represent data and any sort of data really as like some sort of probability distribution. And generative neural networks learn how to create that distribution from a randomness. And so they learn the underlying structure behind the data. So yeah, consider this image of a cute dog. Really consider this image of a cute dog. It's been a long week, but yeah. Okay, so this picture of a dog can also be represented like this vector where n is the number of pixels in the image. I know, not really cute, but whatever. So now we can also consider the vector space, which this vector is a member of. And so the idea is that all dog pictures are a subset, of this n-dimensional real vector space, because all dog pictures of the same like size or whatever are a subset of this space. And this space, it's infinite, but the idea is that it's a probability distribution over this n-dimensional real vector space. Before I move on, did I lose anyone there? Or okay, guess not. But essentially the idea is that that picture of a dog I showed you before, it's just one sample omega amidst countless others, but it is a more probable example in the context of what is a dog in this n-dimensional real space. And so the job of a generative neural network is to learn a transform function from this vector space Rn, the n-dimensional vector space, to the specific subspace we desire, which in this case is dog pictures. And so the subspace is clearly very complex. So it's not going to be like, you just take the first half of it or something. And there are a lot of different variables. And so the transform function needs to be equally complex in order to be useful, which is why in most cases, generative networks are constructed using a neural network, because neural networks are really good at modeling extremely complicated functions. So just to recap the intuition, the idea is that you have an input random variable, which is just random, so it could be drawn from like anything, even the uniform distribution. And so the generative network then takes this sort of randomness and converts it into something that, follows the distribution that you're sort of intended to see. In the example I gave before, this could be you take a vector from the n-dimensional real vector space, and then you sort of use the generative network to sample it into something that is actually from the dog subspace of the real vector space. All right, any questions on this so far? All right. So the most intuitive way to define a loss function for this type of network is to directly match the output that we have with the probability distribution we know for dogs from the data set. And so how do we do that? We don't really have a specific label for that, obviously, because I'm not giving it like a supervised data set where I say this is a dog. I'm just saying that I'm just giving it like sort of examples for how to do this. And we don't have like an explicit representation of like the entire distribution, because that would make the problem redundant, because then we know how the entire distribution is formatted. And so theoretically, any test for how far distributions are based on samples can work. However, in practice, these tend to be inaccurate, especially for really complex distributions, like making a picture of a dog in n-dimensional real vector space. And so this is like a general problem, I guess, with most generative networks, because you're not really able to tell if the output is something that you necessarily want, because you don't really have a good way to match distributions together, especially for really complicated ones. And so the idea is that you need to find a way to determine how similar your output is to the given input distribution, which itself would be a very complicated function. And so another brilliant idea is to use a nonlinear network. So we'll train a separate neural network to determine how close the output from a generative network is to the input distribution. So specifically, this network is called a discriminator network, which determines and the discriminator network is supervised. So it's given a data set from the generated and the true distribution, and it has labels for which samples are from the true distribution and which ones are generated. And the idea is to train these networks simultaneously so that they both improve each other in parallel. And so I'll do another example here. So the idea behind GANs is that you have some sort of latent space. Latent space is another term for random, essentially. And then you sample from that latent space. And so the generator, whatever network structure you sort of put into it, it will generate something from that. It'll generate a fake sample, because technically it's not from the real samples that you have. And so when you have these fake samples, then you can compare them using another neural network. And the idea is that you want this other neural network to not be able to distinguish between real and fake samples. Because when the discriminator is not able to tell the difference between the real and the fake samples, the idea is that means the generator is generating things from the real distribution, or it's getting really close to it. And so that means that the generator has learned how to take random variables and then convert it into the probability distribution we're looking for. However, this means that we also want the discriminator to be really good, because if the discriminator is horrible, then we've gone nowhere. And so the idea is you want to train these networks simultaneously in order to learn. So as the generator learns how to sample from this probability distribution and guess something approximating the real, the discriminator also learns and improves itself on how to determine if a real image is real and if a fake image is fake. All right, did I lose anyone there? Okay, all right, so moving on. All right, so we're gonna kind of go off a whole lot of math here that we're not really going to go into, but I do want to point out specifically the loss function behind, oh, sorry. Yeah, sorry, let me go back to the last slide. So yeah, the input to G is noise. And the reason is because we want the generator to be unsupervised, so, or rather not really unsupervised, but it's dependent upon the output of another neural network based on how good the discriminator is. It'll learn off that. So the generator doesn't learn how to generate like a particular sample. So it's not like taking an input and generating that input's sample. It's learning how to generate a distribution. And so in that sense, it's not really it's not generating off of like a specific point. It's generating off of randomness. Does that make sense? Or all right, yeah, sounds good. Okay, great. So now we'll go into like the loss function. I just want to briefly cover this since as part of the homework, you'll be looking through again, but you won't really be implementing one since they tend to be very, very difficult to implement in practice. I can talk a little bit later about why, but just know that they're very difficult to implement in practice. And so the idea is that you update the discriminator by doing this weighted log function of the improvements. So you sort of want the generator to be a little bit worse than the discriminator, because you want the discriminator to improve its loss as well as the generator's loss. And then you want the generator to improve its own its loss as a respect of how the discriminator looks at it. And so that's this term 1 minus d of g of z. The idea is that the generator will output based off some random thing, something, right? And then the discriminator will try and predict based off that something, whether something is true in the real distribution or in the false distribution. And then it will have some sort of accuracy, right? On like how good it is at determining that. And the idea is that the generator kind of wants to minimize that a little bit. And the discriminator wants to improve that and the generator simultaneously. So that's sort of the reasoning behind this loss function here. If you're a bit confused by this, it might make more sense to go through the notebook that I put for the homework this week, as well as look at some examples online. It tends to make more sense once you've looked at those, or why this loss function is the way it is. But yeah, all right. Does anyone have any questions now? All right, great. And so there are a couple downsides though to GANs. So in theory, they're brilliant step forward for neural networks. However, in practice, like I just said, they can be quite difficult to implement for a lot of reasons. And so the first one is diminished gradient problem. And so the idea is that you're starting off with a very bad generator and a very bad discriminator. But if the discriminator very quickly learns how to distinguish between what is real and what is false, then the generator won't be able to learn. And the reason why is because, for example, say I have like a picture of a dog I'm looking at, or sorry, let's do numbers. So like, say I'm trying to learn how to represent 0 from some random distribution, right? And the generator, the initially will just output 1. So actually, so the G will output 1 initially. And let's say the discriminator is just instantly knows how to determine what 0 is based off the distribution. And so it just says like, yeah, the generator is wrong. You're not, I'm 100% accurate. So that means that you're not doing a very good job, And so the generator gets back the output as in like the discriminator was correct on every single thing and doesn't know where to go from there because the discriminator is correct on everything, meaning that it's not able to figure out why, or where to go from there. Or does that make sense? I might have said it in like a bad way, but the idea is that if the discriminator learns too fast, then it gets too good at figuring out what is true and what is false. And then no matter what the generator gives it, it's never going to be able to reduce the discriminator loss because first of all, it's not going to be able to learn off the discriminator since the discriminator is already really, really good. So that means that it's not going to be able to decrease the discriminator. And second, it's not going to get feedback on what on if its images that's generating are actually approaching the real distribution or not. Does that make sense? Okay. Another problem in GANs in practice is non-convergence. And this is the idea that both the discriminator and the generator never converge. And so it's possible in practice that, you could have a generator that just keeps like oscillating between two different extremes, and a discriminator who also oscillates between two different extremes for the classification. And so both models aren't able to converge based off that because you want both of them to converge, but you also don't want them to converge at very different rates. Like, because as I just mentioned before, if the discriminator converges very fast, then the generator cannot learn. And so you want them to sort of to both converge at an equal rate, which is why non-convergence can also be a problem. And also mode collapse, which is the third problem. The idea behind that one is that the generator just doesn't produce that many things as the output. It chooses to produce only a couple different samples, which produces a limited variety of samples for the discriminator, meaning that the discriminator isn't able to really learn, a distinguishing factor. And so the generator just doesn't learn anymore off that. You can Google each of these problems actually in the context of images. You can see why each of them or what each of them does in terms of the result. Mode collapse, if you've seen things like a deep fake, the thing that creates faces, a mode collapse for deep fake would be a deep fake algorithm that only generates like a particular type of face or something, or a particular type of nose. Things like that would be mode collapse because it means that the generator isn't generating like a very varied probability distribution. It's only generating like a small part. All right. And so now we'll go into this week's second paper. And so the paper is recommender systems based on GANs, a problem-driven perspective. And so this doesn't propose a new model for GANs, but it performs a survey of methods in use for recommender systems in the industry. And it proposes also like a way to list and describe those systems. To be honest, these types of papers tend to be a little less useful in terms of educational content since they're more focused on summarizing information in the industry. But I thought that this would be a good example because it goes into recommended system application specifically. So the paper identifies some key motivations for using GANs in a recommendation setting. The main one being there's a lack of data for many recommendation tasks. So if you have like a user who gets on Amazon once every month or something, that's probably not likely. But if you have a user like that, you don't really have much data for how that user is interacting with your items. And so the idea behind using a GAN is that you could model a user. You could generate some sort of user and use that in order to train your algorithms to improve them. And so that's one way you could use a GAN in practice. You could also use it to like model users' preferences on like unseen data from the user's perspective, because you could just generate what the user could do. And so the main reason they're used is that they can generate new data for training other machine learning algorithms. So recommendation systems obviously are not an exception to this. So the most common use that you find for GANs in industry is to generate user preferences based on previous data, or to generate theoretical items that a user may be interested in based on their past interests. One interesting component of a GAN, one interesting factor in a GAN2 is that they can also be used in components. So this is similar to the concept I was talking about earlier about the autoencoder, where since each network is sort of like a separate component, you can kind of separate them and use them differently. The same thing applies to GANs. So you can use the discriminator portion of a GAN for a different task on its own. So you can use a discriminator portion, for example, to maybe detect a fake user from a real one. If you trained a GAN to generate users, then the discriminator part of the GAN will be really good at being able to detect a true user from someone who is not really a user. And so you can use aspects of GANs in order to determine different things other than the whole model itself. So yeah, one way this could be used in this session is to distinguish meaningful data from the items which your user has not interacted with yet. And that's it for this week's lecture. So like I said, it'd be a bit of a short lecture this week because we're not really going into all the math, and a bit of a short assignment. So this week, there's no coding required. You'll simply be going through a tutorial on GANs and reading the papers I mentioned in lecture. And yeah, that's about it. Sorry, are GANs effective in recommender systems? Yeah, so that's a good question. They tend, in general, actually, I would say deep neural networks do not tend to be used in recommendation systems in practice because of the complexity behind them, because you really have to train them with a lot of data. And for a lot of recommender systems, there's not really that much data on them, as in like data that would be sufficient to train a neural network. So in general, neural networks aren't really that commonly used, but GANs tend to be used in order to generate more data. So they're not effective in the sense of like recommending something per se, but they are effective in making neural networks more accurate, making other algorithms more useful for recommender systems. So yeah. Best algorithm, actually the algorithms we've covered in the first few weeks, Giovanni, would probably be the best ones to use based off their simplicity for the most part. However, a general trend that we see is that neural networks tend to be far more accurate or far better at generating good recommendations, but they also tend to require a lot more processing power. And so for a lot of really like high volume applications, you tend to use methods like collaborative filtering. Those tend to be the ones that are preferred. However, we are seeing a trend based on like just the general evolution of processing power for different applications that more companies are are like advancing to using neural networks because they do tend to be more accurate. So I think we're still in the transition stage where based off the complexity, other like simpler algorithms are usually better for practice, but neural networks do tend to be a lot better, and we're getting to the point where we can use them, in the real world. All right. Any other questions? Or yep, yeah. And so everyone feel free to head out now. Like I said, this week's lecture a bit shorter than usual. Not a bit, but a lot, but yeah. The homework submission for number 6 has an issue. Okay. Sebastian, could you the okay, Sebastian, I'll get back to you on that. I'll check with Andre on the week 6 assignment. Yeah, sorry about that. Okay, so yeah, Sebastian, maybe try again because I feel like other people have submitted the homework, so I'm not sure if it's a problem on our end, but um, I'll check for you. But yeah, and if the worst case comes, Sebastian, you could just send me your solution, and I could manually submit it for you if you want. But yeah,